Peter Molnar. I guess I am an OG. I was probably on, if you were in the previous talk with Brian, I was on a, probably one of these meetups, so I might have been in that picture. I started going like 2012, 2013, I started going to data science meetups. I used to be a computer science professor, then decided, well, I went to these meetups, called myself a data scientist, moved to the industry, spent 10 years there, and then now I'm back in academia. I'm an associate professor with the Institute for Insight at Robinson College of Business at Georgia State University. Okay. Don't hear any cheers right now, but it's okay. And so we have a really exciting data science program. It's a technical program, but nobody is closer to business than Robinson. And so our STEM-based, basically STEM data science program is out of the business school, and we're working with a lot of industry partners together so that our students actually get the value of having practical experience right from the first semester on. So, but what I want to talk today is about how some of the concepts that are kind of diverting the symbolic AI and the neuro AI, basically the Gen AI, large language models, and so on. Everything has been neural network based for the last couple of years, and we had made huge progress there, and everybody's talking about it. But kind of reflecting back is like how the last 50 years or so of advances in artificial intelligence have been, there are other concepts, how we can bring them in and how can they work together. And that's what I basically want to explore a little bit in this presentation here, is how we, the strengths and weaknesses of each of these approaches. It's very difficult to show this in visuals, so here just some words, but the mathematical background is slightly different. So on the symbolic side, we talk about propositional logic and first-order calculus. On the neural network side, this is more linear algebra, gradient descent, so numerical methods. And if you think of back to the history, and actually the first sort of two original high-level programming languages that were created in the late 1960s were Lisp and Fortran. They're pretty much kind of matured around, or the first versions appeared around the same time. Fortran is basically what kind of sort of the grandfather of pretty much most of our programming languages that we can think of, C, Python, CUDA, anything. It introduced arrays, and that became, the arrays of certain types, so we could create vectors and matrices, and that kind of lent itself to numerical computing. Lisp, on the other side, the designers of Lisp had something completely different in mind. They were thinking more algebraic, and having just some type of symbol representing an entity and looking at the relations between different entities and computing that. So that's kind of like the closest that we probably, or like you might see is, or you might think of is like, for example, graph databases. We look at RDF triples or something, we could think of them as symbolic representations. The symbolic side of we have on the neural side, we have made major advances in the last 5, 6, 7 years, partly because the availability of new libraries, GPUs and CUDA, the computational capability and the availability of data, of course, has exploded. On the symbolic side, we haven't really seen these technical breakthroughs yet, but I wouldn't count it out that it actually happened, hopefully happens at some point. So if you think about it, symbolic, for example, graph databases, we have entities, nodes, and relations, vertices between them. On the neural side, we're always just basically thinking vector space, so vector databases come in, so kind of showing that. Some of applications for symbolic computing are, for example, Bayesian networks. This is kind of like a step up for you, those who might not be familiar with that. It's a step up from basic logic tables. So think about the dependency of we have the nodes here represent certain states. Like, for example, is it cloudy or not? And these, in this simple case here, are just logical, they're basically true or false, so Boolean variables. And so basically to see, let's say, okay, what is the likelihood, or is the grass wet? Wet grass is true. It may depend on whether it rains or a sprinkler is turned on, and the rain and the sprinkler might be actually depending on whether it's cloudy or other types of dependencies. So the Bayesian networks is a way we can build some reasoning in there, saying that certain things, if they're either true or false, or have other types of values, and then build these logical dependencies. But with Bayesian networks, for example, we don't really have to just rely on the true or false. We can assign probabilities to that. And these are fairly powerful approaches, for example, that have been used in diagnostics algorithms or programs and applications. But symbolic computing and symbolic AI has basically the advantage built in of the logical reasoning. So it's built on logic, it's built on inference, and there's mathematical foundations like first-order predicate logic, and then what you see here is actually Prolog code. So Prolog is a programming language that evolved around the 1970s to represent, basically for mainly symbolic computing. You can write numeric programs with it, but it would not be the most efficient way to do that. But the idea of representing knowledge, and then from known, and then a way to develop reasoning. So what you see here in this example is very simplistic, but let's say we have some type of entities, and we just call them Pam, Bob, Tom, Liz, Anne, and so represent symbols representing people. And then we have a relationship between them, and that's what you have. It's called a predicate, like a parent. So Pam is a parent of Bob, and Tom is a parent of Liz. So this creates a relationship similar to a graph database. This formalism allows you to do more than just binary connections, but nevertheless, you can come up with some data. That's basically it, the facts. So these are known facts. But from this data now, we can generate new rules. And we can say, for example, that we can define a predecessor. And the predecessor could be a parent, for example, but a predecessor could be also the parent of a parent or another parent of a predecessor. So building these type of rules allows us now to create new and generate new relations. And this is a very simplistic format where we can now use this, exploit this, and ask questions to our system. In this case, the system is very simple because we could, basically just ask, for example, who is the predecessor of Bob, or who is basically who is a descendant of Bob, and find out all parents or all predecessors, pairs of predecessors. So this simple framework, but allows us then, being rule-based, to build larger, more complex problems and solve them. And the beauty of that is it's fully deterministic. So we can, at every time, whatever the answer is, we can explain it. It's all based on logical inference. Another example, symbolic, basically natural language processing, has been for a long time basically purely symbolic. We would represent words or even break them down. You know, if you remember lemmatization or stemming of words, you have basically symbols, and then having categorize them in different parts of speech, and then define grammar trees. And these grammar trees, like basically, these are like formal, the formal syntax or the formal grammar of our language can then be used to parse sentences and extract the meaning from that. So what you see here is on the left-hand side is a sort of very simple grammar for an English sentence, but then it basically allows you to parse a sentence, like for example, the dog saw a man in the park, and based on the grammar tree, now we know what is the subject, what is the object, and we can extract the meaning of this sentence from that. A lot of work has been, there's a huge body of work, of course, that has been done in the last decades. I put WordNet on here. WordNet used to be the #1 for the English language, the #1 catalog. It was not only that it basically became like a dictionary for the vocabulary, but also relations between different words, like what are their nature, are like their adjectives or verbs, what is the antonym, what is the synonym, and so on and so on. So then, of course, on the right-hand side, you have this is just an example of I think this is BERT, like a transformer model. So the symbolic computation has been, has been around for a long time. And if you look at, this is a seminal paper, it was actually a dissertation work by Terry Winograd in 1970 or 1971. He created a blocks world. And it's kind of this, if you heard of it, or if you go through that, the idea is to limit the domain, the knowledge domain of basically the universe, to of course, a very simple problem. So back then, 1970, over 50 years ago, it was a very simple idea of having a table with a number of different blocks, and you have some type of robot arm that can manipulate the space and pick up a block. But even back then, if you read the transcripts, and this is just an excerpt of the transcript, the amount of knowledge that was, I think it was actually already pretty expressive. Yes, I'm talking to Alexa all the time, and for most part, it does what I want to, and it even answers some of my questions. And it's much more, of course, a much broader domain that I can ask for. But this system was already able to process English language, respond, basically take questions, respond in plain English, and it was able to to take commands, like modifying the space, the blocks world, as well as asking questions about that. So it was able to reason for that. It was also able to combine actions and plan. And so a lot of these things that are actually used for solving problems have been kind of introduced in that. It was a very limited domain, but nevertheless, it was, I think, a good start. And there's a lot of development that has been done in that space, and planning and the knowledge representation, that I think we could still benefit from a lot. And so again, this is like the system, the blocks world, kind of works on a state. We have a state space, so any configuration is a node in the space, and then we have some type of, we can define what are transitions from one state to another. Again, you can think of this more as a graph place, a graph in the state graph in the or state space in the logical, in the symbolic domain, versus what we basically in a neural domain we talk about vector spaces. So one of the this is sort of an example in this group of problems, but even in that time frame, Newell and Simon developed a general problem solver. And I was going, the idea is like, okay, if I want to solve a problem, I want to do something, what does it take to get there? Which is actually sort of a very natural way for us to solve a problem. And again, we would break it down. So, for example, taking my son to school, have to drive, is the car working, and so on and so on. So this idea of representing in a discrete symbolic state, we can represent our problem in our problem space, and then have algorithms to solve that. One of the things that, there's no question about it, is the scalability. A lot of these problems, even to this day, have been somewhat limited and have been limited in scope. We have a very small problem space, and most of the rules have been hand-coded. And there's definitely a challenge of scalability that needs to be overcome. For some, like for example, most of these algorithms utilize heuristics to expedite the search through the entire possible space of states. And and that is actually now kind of leading up to where opportunities are. But just to stick a little bit longer around, on the symbolic versus neural, there's still machine learning or learning from data. So for the neural networks is basically the backpropagation algorithm. We compute an error and backpropagate the weights. In the symbolic space, there is inductive logic programming, which is kind of like these rules that I showed you earlier. We can actually define, we can have algorithms, training algorithms to provide data. Here's again a similar example of defining a relationship. In this case, the example is a grandfather, which is a parent of a parent or the father of a parent. And how to come up with the rule based on some known relations, known predicates, that's our base knowledge, and then examples. And these are positive and negative examples. And basically what we want to do is we want to have an algorithm finding different types of rules that might be candidates, hypotheses, and then solve them based on the examples, our training examples that we get. The advantage of this is that this type of training is that we usually can we can get away with many less examples, positive or negative, or it might even work only on positive examples. And then whatever the output is, it is a rule. It's something that we can actually interpret and reproduce. So if this rule is defined and found, it will be the same output for any input. For example, here if the result would be define a grandfather being the father of if you have z, x, z, and y, the grandfather of x and y is the father of some middle person z, or and z is the father of y. So and I'm sorry, I'm actually jumping out. This is of course very wordy here, but there's definitely an advantage in the symbolic AI, which interpretability. We can also code our domain expertise. So if we have, as we think in business rules, we can integrate them directly. The rule-based reasoning allows us to really trace everything. We can explain. We can also ask questions of how something has come to a conclusion, or identify exactly where something, what would change the outcome. What we are lacking, and basically that's the strength of neural networks, of course, is the scalability and that we have, and in terms of like processing large amount of data and training on these data, and not having to do any manual feature extraction or stuff like that. But actually, that's kind of thing like going back and forth. I'm happy to share this. But here's basically one of the key, one of the applications that was basically during the 80s, 90s, was sort of one of the first waves, I guess, of AI, which created a hype, but then also created a low, and we're kind of thinking probably Gen AI, we will have a high and getting a low. Doesn't mean that any of these technologies are completely obsolete. Usually it means there's some expectation which is not quite met, but eventually these technologies and these concepts will just basically go into other types of domains. And so the rule-based expert system is exactly having some knowledge base, having a rules engine that allows to do inference, to define business rules, find business rules, and then allow to, like, for example, question and answer. So common, or some of the popular expert systems, they have been all somewhat in the domain. Like MySyn is, you might have heard about it, is about infectious diseases, to discover them and make recommendation for treatment options. And there have been a couple of these expert systems around. One of the challenges is that they had to basically you have to have an expert who's sort of defining these rules. That used to be done manually by collecting the information. And then to build the knowledge base, which has like rules and facts. Rules engines is not so much of a critical thing. That's basically just the algorithm, how to solve them. There are different ways, but even that could potentially be expanded. And then the user interface used to be similar, like a query interface, which of course we have, now we can have technology, particularly with like, language models, to build out a semantic search where you enter a sentence and that can be converted into a formal query that goes into the system. So just what I highlighted here in red, and this is basically all the things that we have been doing in the last couple of years and made large strides with large language models, foundation models, GPTs, or chat GPTs, and how we can bring them in. Now tapping into the vast source of data and text and what we have, information that we have, to extract the knowledge and build these knowledge graphs and building these rules that we can build in there. So I believe there's a lot of elements, a lot of points where these technologies, these concepts can be combined to basically build more powerful solutions. So I know this word is also pretty wordy, but just basically thinking of how to integrate them, how to use some of the symbolic concept combined with the neural concepts to basically build more intelligent solutions. I think I'm way over time, but thank you so much, and I'm sticking around for questions. So. You can. I can't see anything so blindly. Oh. I think they got away. Can you put it slide back up? But I think we need to clean. So the adding knowledge.
Yeah, adding knowledge shows the knowledge expert. That's the knowledge for the ruler.
Right.
But in the red line, you mentioned like you search the internet.
So I think we can. So the old system did not have. So in the old system, it was or in the classical system, it's experts would manually enter or program that, so they're engineers building these knowledge bases. The idea is, of course, now we can automate a lot of that. So that's for one. I think that's, I don't have a pointer on here, I think. But then on the lower one, in the rules engine, I was thinking of, like, for example, these examples that you do with LangChain now, like building a chat agent that is, using ChatGPT and uses the Google search. And the idea, I didn't go into the rules engine, but the rules engine is kind of similar. It's an iterative process where you find matching information in your knowledge base, and that could be like a natural way to integrate this as well.
Now, my question is that if creating the data by experts, that's kind of awesome, right? But isn't it losing importance when you search the internet? That's the kind of my point. Like you start really good, but once you enter the searching internet, I guess it loses the authenticity.
Yes, so yeah, absolutely. You would have to be careful what you bring in. Absolutely. I mean, I absolutely agree with that. That's still whether you need to control what you come in, and if you just basically look at the search for the internet, it potentially opens up your system to whatever you build in. I mean, this is sort of just really high level, but yes, so you would definitely still, I mean, you still would have to build all these safeguards in there. And I think that comes to the point where we have these different technologies, and how do we integrate them? And of course, they're not one solution, but integrating them to build smarter solutions. So, all right, thank you.